Warahmatullahi wabarakatuh and salam sejahtera. This is the example of Rankine cycle. So if we look at this diagram, we have pump, boiler, turbine and condenser. The liquid will enter the pump at 10 kilopascal with a temperature 38 degrees Celsius, and the pump has isentropic efficiency of 85%, and the liquid will compress up until the pressure 15 megapascal and temperature 35 degrees Celsius. So what happened here? The high temperature and high pressure will enter a boiler. In a boiler, the heat will in a boiler at constant pressure and will going out from the boiler at the same pressure 15 megapascal and temperature of 600 degrees Celsius. So this pressure and temperature will enter the turbine, and the turbine has an isentropic efficiency of 87%, and it will going out from the turbine and the pressure will reduce from 15 megapascal to 10 kilopascal. Okay, and at the condenser, the heat will be removed to the surrounding and the cycle will continue. So the question is determine the efficiency of the cycle and net power output of the plant for a mass flow rate of 15 kilogram per second. So to find the Rankine efficiency or the thermal efficiency of a cycle, we have the formula W work of turbine minus work of compressor over Q in. So here work of turbine is H3 minus H4. So since this turbine has an isentropic efficiency, so we have to put A here. Okay, minus compressor. Since the compressor is also has isentropic efficiency, therefore we choose H2A minus H1 over Q in is H3 minus H2. Okay, so we have to find all this enthalpy for each state. Before we proceed, we have to sketch the TS diagram. How to sketch the TS diagram? First thing first, you have to draw a dome because this problem is about a steam. So you draw the dome and we have two pressure involved, 10 kilopascal at the pump and condenser, and we have 15 megapascal at the boiler and turbine. So we have two lines here. This first line represents 10 kilopascal between condenser and compressor, and second line is 15 megapascal represent the pressure at the boiler and the turbine. Since the pump has isentropic efficiency, so at the exit of the pump we must have 2S and 2A, as well as turbine we have 4S and 4A. Please be careful to write down S1 is equal to S2S and S3 is equal to S4S. Okay, next we have to find the properties at a state 1. Okay, so at state 1, we have pressure of 10 kilopascal with a temperature of 38 degrees Celsius. And we refer to table A5. So at table A5, we have H1 is equal to H HF. Why we use HF? It is because the liquid enter the compressor at the saturated liquid. Okay, therefore we have to find H1 as a HF. Okay, at 10 kilopascal, and HF is 191.81, and the unit is kilojoule per kg. And we also find specific volume. Okay, specific volume given here as a VF 0.001014 meter cube per kilogram. Okay, now we go to state 2. At state 2, okay, so state 2, we know that we have an equation of the pump. The work pump is H2S minus H1. And also we know the work pump is also given in this formula, which is V1 P2 minus P1. So we have to find H2S. Okay, so H2S, we rearrange this formula and we will get H2S, we will get it as a 207 and 01 kilojoule per kilogram. Okay, so I put the volume, specific volume. Pressure 2 is 50 megapascal. Convert it to kilopascal. P1 is 10 kilopascal. And H1 is 191.81. Then I get this value. Okay, so from this state 1 and state 2 it is about compressor. Therefore, we have isentropic efficiency of a compressor given as a Ws over Wa. Okay, then what is Ws? H2S minus H1. What is Wa? H2A minus H1. And given here, isentropic efficiency is 0.85. Okay, and H2S 207.01 minus 191, that is H1, over Q in, H2A, or minus 191.81. Okay, therefore we get H2A is equal to 209.69 kilojoule per kg. So we have H2S and H2A. We have H2A and H1. Okay, next we have to find H3 and H4A.